Hi, this is Lab01, and I'm presenting Lab01, Object in Constant Motion. The video I'm taking is a rolling billiard ball. And so let's briefly cover the experimental purpose. It is to observe the motion of a moving object at the same speed without changing direction. And what I'm going to do is to compare the theoretical, and that's the computational model, on GlowScript, and the realistic scenario, which is the video I recorded, and I used Tracker to track the data sets and generated a graph. So I'm going to compare those two, but they're all about the same object. And let's first cover some fundamental physics principles involved, and they are namely Newton's first and second law. So Newton's second law describes an object in motion under a force, a net force, and Newton's first law states that an object will remain at rest or in uniform motion in a straight line without an external force acting on it. So basically, Newton's first law is a special case of Newton's second law, where it states F equals to ma. In this case, the force equals to 0, and that means the mass cannot be 0, so the acceleration or the change in velocity over change in time should be 0. And that means the velocity should be at a constant. So this is the video, and I chose a billiard ball as the object, rolling at constant speed. It is aligned with the edge, and I used a 30-centimeter ruler for calibration and tracker. So the brief conclusion is it is improbable to maintain an object's constant velocity in real life due to the continuous interactions of the object with the surroundings. And that is to say, there are a lot of interactions happening, a lot of forces, push and pulls on the object, so it is hard to actually achieve the condition of having a net force 0. And this is my GlowScript code. Basically, I used the reiteration of position updating formula, and that is the final position equals to the initial position plus the average velocity times the time period used in traveling. And I can also rearrange it and calculate the average velocity by using the tracker's data, and that is the first and the final position, and I calculated the average velocity and plotted it. And this is basically the computational model that simulates the ball's movement. So coming to the graphical analysis, the above displays the estimated graph, that's the computational model, by inserting the average velocity calculated, and below is the realistic model, the scatter plot with a generated best fit line. And the slope of this best fit line is basically the velocity, the average velocity. It is not completely the same, as it is generated by Excel instead of calculating it manually using first and the last data. And the R squared is the linear coefficient, and it reached 0.9997, which means a very high linear correlation is formed. However, there are points where we can see, circled in red, that do not follow the linear trend. And that means this graph cannot be assumed as a perfectly straight line. And there are also some human errors. You can see the fluctuation here, circled in orange, and that could be attributed to me clicking the tracker, and there could be some errors with that. And the experimental result states that the assumption of having 0 net force is falsified, as the realistic scatter plot does not form a perfect straight line. And that also means the ball has experienced acceleration and deceleration due to external net force acting on the billiard ball. And friction is probably the main one that made the ball slow down at the end. And there were some errors in the experiment, including human error, such as uncertainties in tracking, the ball wasn't moving in a perfect straight line, and calibration errors. So I can increase the trial numbers and the frames per second of the video to reduce this error. And another one is camera angle, which may not have been perfectly at 90 degrees with the surface that the ball is rolling on. So I could use a spirit level to measure if the phone or the camera is perpendicular to the surface. And the what if question. So what if I flip the x and y axis? Flipping the x-axis means symmetrically reflecting the graph in the y-axis. And that indicates time accumulates negatively. And flipping the y-axis, and that's the position axis, means symmetrically reflecting the graph in the x-axis. That indicates the billiard ball travels in the opposite direction. So before, if it's traveling to the right, we can say that it's traveling to the left. And the what does it mean question Is it possible to say how many pushes and pulls are added together to give a zero net force in the case that you observed? And the conclusion is actually it is highly improbable to determine all the pushes and pulls of an object because not only it is interacting with, for example, the table, and that's the surface friction. Also, there are some gravitational interactions between the ball and all the surrounding objects. So it is impossible to say.